Hello everyone, today I am going to explain about the block diagram of pulse code modulation. So before going into that, so here we have the pulse modulation. Under that we have pulse modulation. So we have pulse analog modulation and pulse digital modulation. So here we have pulse analog modulation and here we have pulse digital modulation. So whatever it may be the modulation, here pulse modulation means, okay, so here we have pulse modulation, under that pulse analog modulation and pulse digital modulation. So under this pulse digital modulation also we have the different types of modulations. That is, first one is the pulse code modulation. And next we have is DPCM. So this one is called as PCM, pulse code modulation. And next we have DPCM, that is differential pulse code modulation. Differential pulse code modulation. So that is DPCM we call. Okay. So next one is the delta modulation. Delta modulation. So this one in short form we call as DM. Next we have the last one, that is adaptive delta modulation. Adaptive delta modulation, that is ADM. Okay. So this is how we can classify the pulse modulation into pulse analog modulation. So under this we can have PAM, PPM, like the pulse amplitude modulation, pulse position modulation and pulse frequency modulation we have under this analog pulse frequency modulation. So this is the types of pulse analog modulation. So now we have what? Okay, so we have here pulse digital modulation. Under that we are going to study about the pulse code modulation and the differential pulse code modulation and delta modulation and adaptive delta modulation. Each advantage and disadvantages of each one, and to overcome the disadvantages we can go for the next level, that is DPCM. To overcome the limitations we will go for delta and adaptive delta modulations. Okay, so this is about how we can classify this pulse digital modulation. Out of that I am taking here the pulse code modulation and I am going to discuss about the block diagram of this pulse code modulation. Okay, so here the pulse code modulation basically consists of three sections, three parts. One is the transmitter section, and the second one is the transmission part, and the third one is the receiver section. Okay, so here this part is called as, this is the one, first one. So the basically this pulse code modulation can be classified or can be consist of three parts, that is, one is transmitter part, and next one is transmission part, and third one is the receiver. Okay, so here this block diagram of PCM can be divided into three parts. One part is the transmitter section and another part is the transmission part and the third one is the receiver section. So this one is called as transmission path. Okay, so here we'll see individually each section, that is transmitter section, transmission path, and next the receiver section. Okay, so in the transmission section we have the different blocks. Okay, so what is the first one? That is analog message signal source or continuous signal source. analog signal, or it is another name is there here, that is continuous message signal. Continuous message signal generator or the source, continuous message signal source. So the output of this analog message signal source or continuous signal source is a analog signal. Okay, so that analog signal is given, the output of that source will be given to the low pass filter. Then why we use the low pass filter? Okay, so here the low pass filter is used to remove the higher frequency components. Okay, so why we use? It is used to remove the higher frequency components. Remove higher frequency components. Okay, so why we use this low pass filter? That is nothing but to remove the higher frequency component. What is the higher frequency component? Suppose if I consider omega is the highest frequency of the message signal. Okay, so suppose if I consider omega is the highest frequency of message signal. Then if I passes this analog signal through the low pass filter, whenever there is a high frequency component will obtained at this point at this low pass filter, so that is the high frequency component will be greater than the message signal frequency, message signal highest frequency. Okay, so here if any case the output of this analog signal consists of the highest frequency of message signal, that means greater than the highest frequency of the message signal omega, so then that type of signals will be eliminated by using this low pass filter. That is the significance of low pass filter. It will remove the higher frequency components that is greater than the message signal highest frequency, here omega. Okay, so because of doing that, that means filtering of that high frequency components, we can avoid the aliasing effect. Okay, what is aliasing effect and all those things we will see next. Okay, in sampling process. So here what is the significance means for this low pass filter is it will remove or it will filter out the very high frequency components that are greater than the highest frequency of the message signal. Due to this we can remove the aliasing effect, we can reduce the aliasing effect or the overlapping of the different signals. Okay, so that is the significance of low pass filter. Then that low pass filter output is given to the sampler. Okay, so under this sampler, so what we will do? Under the sampler we will do the sampling process. Okay, so what is sampling process means? Sampling process means it will divide or it will convert the continuous signal into discrete samples. Okay, I am not telling discrete signals, so I am telling that it will convert, the sampler will convert whatever the continuous signal or analog signal that we are applying from the source low pass filter. So it will convert this sampler, it will convert this analog signal into its corresponding discrete samples. Okay, its corresponding discrete samples. Okay, so here the sampler will convert whatever the output of low pass filter, that is analog signal, into its discrete samples. Okay, here we have different types of sampling methods or sampling techniques. So one is ideal sampling, and the second one is natural sampling, and third one is flat top sampling. Okay, so you can observe clearly here what is ideal sampling means. Suppose the wave is like this, the input analog signal is like this. So at each and every point it will divide the sample. So this one is one sample at this time period. In this time period T1 we have two samples. So this one is one sample and this one is another sample and this one is another sample. Like that it will divide whatever the continuous signals we have, that will be into discrete samples. Okay, So here if you observe that this one is the ideal sampling and here we have the natural sampling. So natural sampling also almost same as that of ideal sampling. So if you consider this, okay, so here it is giving that samples means this one is one sample, and again at the T1 and T2 and T3 and T4 and at each and every point of time, or at each and every time, so it will convert, it will give say one sample. So that is nothing but the ideal sampling. But here if you observe this one, here the amplitudes are shown like this. Okay, natural sampling. Here the amplitude of the analog signal is less, so we have the sample like this. And next one is, it is increasing the amplitude, here it is decreasing like this. So whatever the signal amplitude is there, it will follows that amplitude and it will divide the continuous signal into the discrete samples. Okay, this is what natural sampling. But here we have flat top sampling. Okay, flat top sampling means it will be, there is no up and downs, or there is no, if you consider this sample in natural sampling, at this point we have some amplitude for this sample, and at this point we have another amplitude for this sample. So here in flat top sampling we will make all the samples that are under or that are between a time interval consist of equal amplitude. Okay, so here if you observe between this time from this point to this point, there is a increasing in the amplitude. Here we have small amplitude, it is increasing. But here in flat top sampling it is not the case. So it will flat, that means it will equalize all the amplitudes between the time interval or between the given time interval. So this sample time interval is this one. Under this, whatever the samples we have, so their amplitudes will be flattened, that means equal. So that is nothing but flat top sampling. Like this, whatever the analog signal we have, so it will convert those analog signals into the discrete samples. Okay, and after that the output of this sampler, that means this one or this one, depending on the application, will use the natural sampling or flat top sampling. So these will be given to the quantizer. Okay, so what the quantizer duty here? Quantizer will group, or it will convert the total discrete samples into set of samples. Okay, set of discrete samples. Okay, so here if you consider, these are the samples what we have ideally, and what this quantizer will do is it will convert all the sampler outputs into the discrete set of discrete groups. Okay, suppose this one is one group here, this set, because it consists of amplitude, and next it will convert, this one is one quantizer level, or it will assign the sampler output is given to the quantizer, and quantizer will assign, depending on the levels here, it will assign some group. Okay, or it will group all the discrete samples. So that is nothing but quantizer. So it will assign the group of discrete samples and it will assign some quantization level to them. Okay, so after that we have here the encoder. So what is encoder? Means the encoder will encode the data or the quantization levels what we have, that is from output of the quantizer. Okay, so what is encoder means here? It will assign, suppose here we have from this point to this point we have some amplitude. Okay, so it will assign some bit, binary bit to that particular group or particular set of samples, set of discrete samples. So quantizer will provide set of discrete samples. For each set it will give, the encoder will give some binary representation. Okay, so whatever the quantizer output we have, for that output it will provide the digitization. It will provide the digital representation. Okay, so the encoder output is what? The encoder what it will do? encoder will do what means here, for it will assign a binary representation or binary for binary data representation for the quantization levels, whatever we got at the output of quantizer. So the output of this encoder is a digital representation of whatever the signal we are having, like this. It assigns some values, that is digital values or binary values. So the output of quantizer is given to the encoder, and encoder will provide the binary representation of the output of this quantizer. Okay, so what it will do? Encoder will assign the binary codes or the binary representation of the output of the quantizer. Okay, so that is about the output of encoder, and this output of encoder we will call as PCM output. So this block is also called as this transmitter section. We also called as what? The PCM generator. Okay, so what is this transmitter section? Is nothing but PCM generator. So from this point to this point we can use from, if you consider this one, it is converting analog to digital conversion. So the analog to digital conversion is done by low pass filter, sampler, quantizer and encoder. And the output of encoder is nothing but the pulse code modulation data or signal, PCM signal. Okay, so that PCM signal or the output of this PCM generator is given to the transmission path, that is given to the channel. Okay, so here what is transmission path? Generally transmission path means from this point to this point, another point if you move, that path is nothing but transmission path we call. But here also we are calling that one, that is the transmission path is present between the transmitter and receiver. Okay, so this one is the transmitter section and this one is the receiver section. In between transmitter and receiver we have the transmission path. So this is the transmission path. Under this transmission path we are going to use regenerative repeaters. Okay, why this regenerative repeaters we are using means to avoid the noise effect. Okay, the main concern here why we are going to use the regenerative repeaters in the transmission path is to avoid the noise effect only. Okay, so whatever the distortions that will be added due to noise, that can be avoided by using this regenerative repeaters. Okay, so here the PCM output from the PCM generator is given to the regenerative circuits or the transmission path, and here we have the channel. Okay, so the output of this generator is given to the given as the channel input or given to channel. Okay, as channel input. The output is given to the channel input. It consists of regenerative repeaters here. So they will avoid the noise effect. They will eliminate the noise. So and produce the actual signal, or they will keep the PCM signal as it is. They will try to keep the PCM signal as it is without affecting with the noise. So here the output is given to the channel and the channel output is given to the again regeneration circuit. So this one is the regeneration circuit, because if you consider whatever it may be here, if you are using regenerative, they will reduce some part of the noise effect, but the output of the channel will be affected with some noise. Okay, so from that noise signal, affected noise signal, we have to regenerate the PCM signal here. So whatever the disturbed or whatever the disturbance that is obtained for the PCM signal due to the noise can be eliminated by using regeneration circuit, and we will retrieve or we will regenerate the PCM signal from the output of the channel. Okay, so for that case here we are going to use regeneration circuit. Okay, so the output of this regeneration circuit is given to the decoder. So what encoder will do here? The encoder will convert whatever the quantization level or set of discrete samples into its corresponding digital representation or binary representation. So here we got this one as binary representation at the input of the decoder. So this decoder will convert that binary information into the quantizer levels or the discrete sample levels. Okay, so that is given or passes through the reconstruction filter. So reconstruction filter is also a low pass filter, because here the output of this decoder is given to the reconstruction filter. So the message signal frequency is less. So those message signal frequencies can be retrieved or reconstructed by using or by passing the output of this decoder through the low pass filter. So that is the output of the low pass filter is nothing but actual analog signal. Okay, whatever we have sent. That is what this is nothing but the pulse code modulation receiver section. Okay, so here we have seen what is the regenerative circuit. So that regeneration circuit consists of amplitude equalizer. Basically it consists of 3 blocks. That is, first one is what? Amplitude equalizer, and the second one is decision making circuit and timing circuit, and finally we will get the regenerated PCM signal here. At this point we will get the regenerated PCM signal. Regenerated PCM signal. So that is given to the decoder. Decoder will convert that one into discrete samples. Okay. So here the output of channel, how this regenerator circuit will operate. Here the output of the channel is given to the amplitude equalizer. Then what is the duty of amplitude equalizer? So here 1, 0, 1 like that we have before sending to the channel. So it is like this. Okay, it is a pulse wave. So whenever a noise is added, this will becomes like this. There will be some disturbance or spikes will come. Okay, so these spikes or these disturbances can be eliminated by using this amplitude equalizer. So it is passes. This is passes through the amplitude equalizer. So it will gives again the like this. So here whatever the noise that is created here, that is given to the amplitude equalizer, and at the same time before going to this amplitude equalizer we will amplify the output of this channel, and because of that the noise is also amplified. Okay, so before going into the amplified amplitude equalizer, so we'll give the output of the channel here for the amplifier. Okay, so because of the amplification, so with the signal amplification at the same time noise is also amplified. So due to that the amplitude of the noise will also be increased. So to avoid that one, so we are using amplitude equalizer. And next that output of amplitude equalizer is given to the decision making circuit or timing circuit. Okay, so here the decision making circuit depending on the timing circuit, what it will decision making circuit will do is, whenever this timing circuit will gives a pulse, so it will takes the decision which sample or which from which point to which point we have to consider these samples that is given by this decision making circuit, but the timing is given by this timing circuit or time extraction circuit. Okay, so depending on the time extraction circuit pulses, so there will be a samples will be considered. That is nothing but the regenerated PCM signal for us. Okay, so this is about the block diagram of this pulse code modulation or the elements of pulse code modulation. Okay, so thank you for watching. Subscribe our channel.